In this video, we'll give an overview of evaluating trigonometric integrals. Now, what we mean by trigonometric integrals are integrals of the form sine to a power, cosine to a power, or tangent to a power, secant to a power. And the first observation that I'd like to make is if you want to evaluate integrals of this form, there are several identities that you just have to know. So two of those would be the half-angle formulas. Cosine squared x is equal to 1/2 1 plus cosine 2x, and sine squared x is 1/2 the quantity 1 minus cosine 2x. And maybe one way to help you remember the formulas is that they're nearly identical. The only thing that changes would be the plus or the minus. Cosine, the same thing, so plus. Sine squared, different than cosine, so it ends up being a minus there. You also need to know your Pythagorean identities. Cosine squared plus sine squared equals 1, and 1 plus tangent squared equals secant squared. I find that students typically remember the Pythagorean identity cosine squared plus sine squared equals 1, and note if you remember that one, you get the next one for free, because what we can do is just take each term in this Pythagorean identity and divide it by cosine squared. And when you do that, you have 1 plus sine squared over cosine squared, which is tangent squared, equals 1 over cosine squared, which is secant squared. So now on to the integrals we would like to evaluate. So some general guidelines here for evaluating integrals of this form, sine to a power, cosine to a power. And it really seems like a lot's going on, but I'll try to break it down from an intuitive perspective here. So there's really kind of three cases to look at with the powers of m and n. One of those powers is going to be odd, the power of cosine and or the power of sine, and if not, they're both going to be even. So if either power is odd, we take the same approach. So if the power of cosine is odd, the idea is that what we are going to do is save one of those cosines. So that plus 1 becomes the cosine that we save. And then the remaining cosine squareds, so it would be cosine to the 2k, so cosine squared to the k, we rewrite as 1 minus sine squared. And the reason we do this is because then that leftover cosine x dx can play the role of du, where the sine is going to play the role of u. And we think of this as kind of a power reduction technique. You know, we're reducing that power of cosine down to save that du, rewrite the remaining cosines in terms of sine. The exact same thing if the power of sine is odd. What we would like to do is save that extra power of sine, which is going to play the role of du, and then we rewrite the remaining sines in terms of cosine. Then there's the case of both the powers of sine and cosine actually being even. So if the powers of both cosine and sine are even, then what you need to do is use those half-angle formulas we previously discussed and rewrite everything in terms of those, algebraically expand, and then integrate. And the section on trigonometric integrals contains several different examples of this. A similar approach can be taken when we are integrating tangent to a power, secant to a power. But here it's not quite as nice of a dichotomy. What we can do is give guidelines for when the power of secant is even, the power of tangent is odd, and then in general maybe something you can think about if not. So if the power of secant is even, what we are going to do is take a square of secant and leave that over. It's going to be our du. And then the remaining squares of secant we can rewrite in terms of tangent via the Pythagorean identity. So just like we did with the sines and the cosines, but now with tangent. Likewise, if the power of tangent is odd and we have a secant available, what we will do is take that leftover odd power of tangent and save it along with one of our secants. Then we take the remaining even powers of tangent and rewrite them in terms of secant and do the u substitution, u equals secant x. Now if both of these methods fail, as in we cannot apply them, one thing you could always try to do is convert in terms of sines and cosines. So let's look at a simple example illustrating this. So in the integral that we have an odd power of sine. So we said what we're going to do is take one of those powers of sine, and we are going to save it to play the role of du in a moment. So we save one power of sine. The remaining powers that we're going to have are even because we started off with an odd power. And we rewrite those in terms of cosine. So sine squared is 1 minus cosine squared. And now that we've done this kind of reduction of power technique, we're in an ideal situation to do a u substitution. We'll let u be cosine so that du is minus sine. So we have the cosine here is going to become a u, cosine squared is going to become, I guess, both u squared, and the sine x dx is going to be minus du. So converting solely in terms of u's, we have a minus sign coming from that du. Then we have 1 minus u squared times u squared du. And now this gives us an integral that only contains powers of u's, which is extremely reasonable for us to evaluate. So minus, and then we'll have 1/3 u cubed minus 1/5 u to the 5th plus c. And our last step here will be to distribute in the minus sign and resubstitute in u equals cosine. So we'll have 1/5 cosine to the 5th x, and its sign is positive because we've taken the minus and distributed it in, minus 1/3 cosine cubed x, all plus c. And once again, as long as either the power of sine or cosine is odd, this exact same technique can be applied.